Good morning, everybody, and welcome to another session of me programming daily. Today we'll be focusing on drakon render again, and as a follow-up from yesterday, I have a little correction to make. Yesterday I proposed that let's take a look at the code first. Yesterday I proposed that those valent points that we talked about should be inserted at positioning time. But today I'm more and more convinced that they should be injected into the diagram just after the algorithm has read the input, simply because the the positioning of icons should be made much more simpler if we do it at input time. Um, at the positioning time, it feels like we would have to reposition again. At input time, it's just way simpler. So this is the first correction I wanted to make, and I think I have a clear picture of how I want to alter the algorithm now in order to make it work with valent points, and in order to achieve our bigger goal, which is to make these connections look like real drakon diagrams. So I'll try to explain it using very simple text files. I don't have a name for this yet. I apologize. It's still very early in the morning. I don't have a good name for that operation yet, but what I'm thinking is to rebalance, let's call it rebalancing, to rebalance the directed graph in order for those longer stretches of skewers or connections not to be present at all. What I mean by that is in graphs that my algorithm renders today, it is possible to have longer stretches with just nothing in them, while in the canonical drakon implementation, every available space in the graph should be filled either by a valent point or by an icon. So what my realization is since yesterday is that what my algorithm is missing is just valent points. So that if you inject valent points where they should be according to the canonical representation, connections like that will no longer be needed or present. Or connections like that will not be a special case. They would just be a natural consequence of a question icon connecting to a valent point that is hosting no icons, and then the valent point connecting to the next available dependent, which is another question. So to illustrate what I'm going to attempt on paper, I'm going to produce a very simplified text-based chart. And this implementation is probably going to take me at least a week. So that will keep us busy for another stretch of time. But I feel we're progressing towards something bigger than I initially planned. And I hope it's going to be very useful one day to somebody. Now, so what I'm thinking of doing is, let's say we have input diagram that looks like this. We're not going to name icons. I just want to show you something like this, where X is just an icon and this pipe is a skewer. So let's say, or you know what, maybe let's give them identifiers. So let's say icon x2 has two dependents. How do I represent this? Plus. we have icon x5. To leave ourselves a little bit more space, I'm going to space them out like this. So if if icon 5 has one dependent and that's icon x3, the connection will be pretty awkward, and it would be something like this. X, here we would have a pipe, and that pipe would go somewhere here. So that would be an X, and here the connection would be something like this. So to represent it as text, let's save it on the desktop. Text will be fine. That's fine. The dependence would be listed like so. X1 has one dependent, and that's X2. X2 has two dependents, and that is X3 and X5. X3 has one dependent, and that's X4. And X5 has one dependent, and that is X3. So this is what we have today. The diagram would look like this. And what I'm proposing is, if we have a situation where one icon is a dependent of two different icons, and the lengths of paths that lead to this icon is different for those two parent icons, it means that we have to rebalance this connection and insert a valent point in this place. So to illustrate this, this is the proposed approach. So we have x3, and we see it is a dependent of x2, but it is also a direct dependent of x5. So it means that from x2 to x3, you can get in two different ways. Okay, so if those ways, or if those paths are of different lengths, it means that we need to rebalance the graph and make sure that all paths leading from this icon to this icon are of equal lengths. So that in order to achieve that, we just insert a valent point like so. Let's call it V1. And it is not an icon, it's just a point. So in that case, since x5 is going to remain where it was, x5's connection is going to get much simplified, and it simply will go like this. And bear with me. Two, three. Yeah, something like this. And now the graph looks much better, and it is much more aligned with how the canonical drakon would represent it. So let's just double check that it's really the case. Let's go to the documentation. And find an example that would work exactly the same way. I think it's one of those later graphs. Yeah, here. So this is our x2, this is our x5, and this is our x3. So here exists an invisible valent point that it's only available and visible at design time. Of course, we do not have design time. Our design time is the time when you prepare your JSON input. But what the user does not have to be aware of is we are going to artificially inject a valent point into the graph. That is going to be rendered as maybe in debug mode as a slight dot, but ultimately is just going to be rendered as nothing, so that it looks like it's just a skewer here, not a connection. That way, we will fix the positioning of the icons in the graph. And I'm thinking if we apply the same strategy to the entire graph, we shouldn't have problems with positioning of bypasses like this, right? Because here would exist an invisible valent point. Therefore, we wouldn't need a special case just to prepare this bypass. Okay, so I think we're good. Now, the trick is to implement this, and but before we get to the implementation, let's just recap in simple terms what I'm going to do. We are going to rebalance the graph so that the paths from any icon to any icon, all the lengths of paths, or all the lengths of all paths from icon A to icon B will always have to be of equal lengths. Meaning there's always going to be a valent point in the graph where a dependent is missing. Okay, so in our case, we're only missing one valent point, but if we had more icons here, like x5 with one dependent, x6 with one dependent, x7, and that only has one dependence of x3, we would have inserted 3 valent points, v1, v2, v3, and we would render them as either nothing, or maybe in a special debug mode, we would render them as dots. So I hope that makes sense. I think this is a pretty general plan that should work for all graphs. Now, the implementation I have in mind is divided into 2 steps. Step number 1 is to try and just manually add those valent points to the input JSON here and render them for now as just regular icons. Later we can change the type of a valent point to an actual valent point, but for now, just for the sake of rendering or being able to render, let's treat it just as an icon type. That's the first step of my implementation. And the second step is to provide an algorithm that finds those paths between icons. So to recap, if we have a path from x2 to x3 that leads either directly to x3 or indirectly through x5, we would have to make sure that they are both of equal length by inserting a valent point between x2 and x3. So that's the first step should be pretty doable. It should take me a day or two, but the algorithm of finding paths will require some more thinking, and I don't have a good idea for it yet. So today, let's focus on just providing those valent points in the input and maybe rendering them quickly if time allows. So let's start in the record, in data types. Now, for now, we are going to treat the valent point just as an icon type, just to be able to render it. Starting with this part of the algorithm, meaning from rendering, will give us a very short feedback loop during which we'll immediately notice where valent points should be inserted. So that's... So I think in this real life diagram, we will require two valent points. One placed between this question and this action in order to rebalance this section, and one placed here, or maybe more even, and one placed here to rebalance this section, and also one placed here and one place here. Okay, but we'll get there. So we have valent points in data types. Let's go to records. Here we need to do nothing, I think. Yeah, I don't think this file has anything to do with icon kinds and basing any logic on icon kinds, except, of course, the title icon. We will have something to do in the render part because, at least for now, I want those valent points to be represented just as dots or circles. And the layout engine, I don't think layout engine has anything to worry about. So for now, let's build it. I love getting warnings like that. Pattern matches are not exhaustive, which is great. 198. So this is probably telling us, okay, you're pattern matching on all icon kinds, but you've implemented a new one, which we don't know how to render yet. So we're going to provide an implementation for a valent point, coordinates, text description, and let's go here. Oh, this is a where. All right. What's going on? Oh, so a valent point will be much easier. So let's maybe copy it from something like a title shape. And for now, let's find this in the diagrams library. Do we have a circle? What? That's a circle. Let's make it the famous 0, 1. Oh, sorry. I think this is correct now. Yeah, this looks more correct, I think. Okay, so what we need to do now is to inject a valent point into the input. So let's refresh my memory. It should be between remove the brain question and remove the brain action. Or remove brain and remove the brain. So here between question 6 and action 8. So now it depends on remove brain, which is question 6, depends directly on icon name 8, which is remove the brain. Let us inject the valent point here. Because technically this is the first dependent of remove brain, and remove alternative, which is here, is dependent number 2. Let's call it V1. Oops. So here we won't render text, I think. Let's call it 6V1. Or maybe just V1. And it is going to only have one dependent, and that's 8. And here we are depending on V1. So I think that's it. And if I haven't missed anything, this should render just fine. Oh, there's a problem. Did I leave the change from yesterday here? What is this? Let's check if we inserted everything here correctly. Valent point. Oops. This looks correct. Problem interpreting diagram file. Icon. Did I make a mistake here? Icon name V1, dependence V. It looks like we're building it 3 times. Why? And it looks like we still have the old code in here. I only want the real life diagram one. Yeah, it definitely has still the old code. No. What is going on? You know what? I can figure this out off camera, but I think we have a solid foundation for the changes. We have the new data types. We have made changes to the input. So starting tomorrow, I'm hoping to have fixed this by tomorrow. Starting tomorrow, will be proposing a shape of this algorithm that checks the lengths of all available paths from any icon A to any icon B, which could be a lot, and will detect if there are any shortcuts available. Right? I think we can wrap it up for today. Thanks again for sticking with me. I hope this was useful to you. And you'll see me during the next one. Have a great day. Bye bye.